kind of scary pathways of carbohydrate metabolism. What do you mean? Well, here's the thing. I know I'm going to trip over this one. It's okay. It's okay. We're going to discuss a pathway that's very significant in terms of many aspects that you will be asked for. If I ask you, is it good for people to take honey, especially type 2 diabetic patients? Honey.
Yes.
Is it good for people to take, especially diabetic patients, take juices?
No.
But if I tell you juice, do you think it elevates or takes the concentrations of glucose high? Does it do that?
No.
It doesn't. So why can't it be? Why is it bad? Do you see what I'm saying? So the question is, it doesn't induce hyperglycemia as if you were taking glucose. That is fruit, corn syrup, honey. Honey mostly is fructose, but it does not induce hyperglycemia. So why is it bad, or why do you think it's not that great? I'm going to answer it simple. Everything that is moderate is a good thing. So honey, yes, take honey. It does not induce hyperglycemia, but don't take too much of it. And we're going to explain all these pathways. We're going to discuss some inborn errors of metabolism. You're going to hear a lot about it. There's more than 600 of these. And they could start, actually the minute you have the baby delivered, you could see some effect that there's accumulation of some of these metabolites that would induce a lot of side effects, a lot of conditions. So we're going to describe some of these inborn errors of metabolism today. At least know the term, inborn error of metabolism. Can you screen for these inborn error of metabolism? Yes. But if you want them all, you send a sample to Germany for $500. Here, they can go, right now, 27 in the King Faisal Specialist Hospital. They can go up to 97. They're trying to improve to 97 metabolites or screening for these inborn errors of metabolism. And actually, other private hospitals, it's a good business, because that's why other hospitals now, they're trying to do the inborn error metabolism screening, but the results of this is that there's so many labs, not that many samples. It's not mandatory to maintain or to measure all these metabolites to see if there's any inborn error of metabolism. So I told you, what's the simplest way of checking out to see if everything is going well? Weigh the infant in the morning, in the evening, and this is why they don't release the baby unless he starts gaining some weight, so that they know that his metabolism kicks on. And also they have a check after 3-4 days to see if he still continues to gain weight. This is kind of way of looking that all the metabolic pathways are functioning. Now we have the learning outcomes. Why do you call it learning outcomes? Ask the medical education people, don't ask me. To me, these are objectives. But they like to call it learning outcomes. We're going to describe the glucose. So everything we've been studying, glucose, glycolysis, gluconeogenesis. Then we have glycogen synthesis, and then it's all about glucose. What about the other sugars? How much do you think fructose constitutes of our diet? Fructose. 10% of our diet is fructose. Fructose, especially sucrose, because sucrose is disaccharide that gives you fructose and glucose. We eat too much sugar, right? How much sugar there is in that can of soda that you're drinking? 37.5 grams in that can of soda. Imagine having 73 grams of sugar that you're drinking in that can of soda. Imagine if you go for super or large Pepsi, that max. You go for the huge jug of Coke there. How much sugar you're eating there? Funniest thing, when I went to Paris for a visit, I went to McDonald's. So I want the max. I want to. Every time you go to these fancy restaurants, you take small filet mignon, and you end up paying 100 euro for a small amount of food. So I said, let me go to McDonald's. So I said, give me the largest one you have, drinks and so on. And they gave me this small Pepsi. I was like, this is the max you have? It's like, yeah, this is the max. I said, what about the small? Is it miniature or Pepsi or what? But anyway, so after finishing the McDonald's, I ended up going basically to another Burger King, so try to finish my meal. Anyway, but the thing is, we eat too much sugar. And I'm not talking, when we say sugar, that's sucrose. That gives you fructose. This is why it's very important lecture, because we're going to talk about many aspects. Why is it that diabetic patients have kidney problems? Why is it diabetic patients have eye problems? Why do we have a lot of problems with diabetes? And the word is sorbitol, that comes from fructose, that we will describe as well. Okay? Also, we have lactose intolerance. What's the percentage of lactose intolerance you think right now people say? Around 70% of people. This is the latest study. 70% of people have lactose intolerance. Does this mean that people cannot have galactose?
No.
Because we need galactose as part of the milk, right?
Yes.
Galactose is part of the milk. So how is it that mothers still can make milk even though they cannot tolerate galactose? Right? So we're going to talk about lactose synthesis in the body and how glucose can be converted to galactose that then gets converted into lactose, and that's how moms can produce milk. But also, we're going to describe a reason for infertility, for men infertility, coming from metabolism of galactose. Anyway, these are the learning outcomes compared to the ones that you had for the TBL 2 and 3. We're trying to put more of these objectives. We need to describe the mechanism of fructose metabolism, disorders associated with deficiencies in fructose metabolism, outline the conversion of mannose to fructose 6-phosphate, formation of fructose 6-phosphate from glucose via sorbitol. Then we need to describe the mechanism of galactose metabolism, disorders associated with galactose metabolism, outline lactose synthesis in mammary glands. It looks so many. I'm going to summarize 90% of the lecture in 2 slides. You remember it? The rest is just nothing other than repetition of the same 2 slides. Simple. So we do have different types of carbohydrate, monosaccharides, disaccharides. That includes, other than glucose, lactose, which is milk, sugar. We have sucrose, which is sugar cane, sugar beet, and other fruits. Fructose, various fruits, honey. Also sorbitol, which is sugar alcohol. So when we say sugar alcohol, is that bad? My wife's cousin, she is diabetic, type 1 diabetic, so she can't take candy, chocolate. And this is sad. So I said, okay, no problem. I was on my way back from from US. And then I brought with me chocolate bars with sugar alcohol, which is not present here in Saudi Arabia because they see, oh, sugar alcohol, there's alcohol word. It's got nothing to do with alcohol. All what it is, it has hydroxyl group. That's it. Simple. But what happens is that it has low glycemic index. It does not go high in circulation. So this is why diabetic patients can have it, especially type 1. And it's present everywhere, all over the world, except here because you see the alcohol word. That's a no-no. But, if you know someone who's diabetic and you would really make him really happy, that's what happened to her cousin.
Sugar alcohol.
Just give him these chocolate bars that are for diabetics, and they have a lot of sugar alcohol. It's got nothing to do with alcohol, but at least they can enjoy. It's really tasty, and it tastes almost like chocolate, real chocolate. Anyway, this is the first slide. I said 2 slides. If you remember them, 90% of the lecture coming from these slides. And you know most of it. Why? Because you know glycolysis. Hopefully you still remember your glycolytic pathway, right? Glucose is converted to glucose 6-phosphate, right? Which enzyme? Hexokinase or glucokinase. What's the difference between hexokinase and glucokinase? Hexokinase, all the cells. Glucokinase, the liver, and it is stimulated by insulin. These are the difference between the two. But also hexokinase can phosphorylate carbohydrate other than glucose. But gluco, from the name glucokinase, only glucose. Hexokinase can phosphorylate fructose and galactose, other monosaccharides. Whereas glucokinase, from the name glucose, only can phosphorate glucose. So we get glucose 6-phosphate. It's converted to fructose 6-phosphate by which enzyme? Glucose to fructose. That is isomerase. Glucose to fructose. That's isomerase right there, right? And that is glucose 6-phosphate isomerase. Fructose 6-phosphate, fructose 1,6-bisphosphate. Bis di, meaning 2. 2. So we have fructose 1,6-bisphosphate. Which enzymes? Phosphofructokinase 1, fructose bisphosphate phosphatase, reverse. So is this regulatory mechanism?
Yes.
Why?
Because it's reverse.
Insulin regulates PFK.
Oh, okay.
So insulin regulates two things here. Glucokinase and PFK1. Right? I'm going to explain to you why fructose is different and other monosaccharides are different than glucose from this pathway. Now, through aldolase A and B, fructose 1,6-bisphosphate gets converted to two things. Glyceraldehyde 3-phosphate, dihydroxyacetone phosphate. The dihydroxyacetone phosphate gets converted to glyceraldehyde 3-phosphate by isomerase. Triose phosphate isomerase. Glyceraldehyde 3-phosphate now goes to
Pyruvate.
pyruvate. And this is a glycolytic pathway that you already know, so it's not that bad. I mean, you know most of it. Let's see where monosaccharides get into play. The first one, galactose. Galactose gets converted to galactose 1-phosphate through which enzyme? Kinase. I mean, we're adding phosphate group. That's a kinase, right?
Yes.
Galactose 1-phosphate to glucose 1-phosphate. Is it isomerase? No, this time it's uridyl transferase. It's different. We'll talk about it. We're going to explain this pathway more. Glucose 1-phosphate gets converted to glucose 6-phosphate. Which enzyme? Glucose 1-phosphate to glucose 6-phosphate? What do you think? Is it mutase? 1-phosphate to 6-phosphate. Think of glycogen synthesis. Right? Why kinase? You have 1-phosphate to 6-phosphate. Is it epimerase? What do you think? I'll give you a chance until the second slide. Here's the thing. Galactose to glucose 1-phosphate. What do we utilize glucose 1-phosphate for? Glycogen synthesis, right? Before we convert into UDP glucose, right? So notice here galactose can be utilized for glycolysis or glycogen synthesis. Right? So this is where galactose gets into play. That's easy. Mannose. Do we have too much mannose in our circulation or from diet?
No.
Minimal. It's not a big, large pathway, but it gets converted by mannose to mannose 6-phosphate by which enzyme? Kinase. That's easy. Mannose 6-phosphate to fructose 6-phosphate. Which enzyme? Isomerase. So we have fructose 6-phosphate, we have glycolytic pathway. This is where mannose gets in. Now we said fructose coming from diet as what? Fruits, honey, syrup, corn syrup, I'm sorry, and or from sucrose, because sucrose is disaccharide, breaks down into fructose and glucose. Gets into play in a pathway, notice here, that bypasses regulatory pathways, which are PFK and glucokinase, right? Notice here it's coming down from the bottom rather than, it's bypassing these regulatory pathways. So we have first enzyme that converts fructose from the diet or the sucrose into fructose 1-phosphate, kinase, fructokinase. That we can remember. Fructose 1-phosphate, notice here, fructose 1-phosphate, not fructose 1,6-bisphosphate. Gets converted through aldolase B to glyceraldehyde and dihydroxyacetone phosphate. The way to remember it, we have aldolase A, aldolase B that gives us dihydroxyacetone phosphate, but also gives us glyceraldehyde 3-phosphate, so 3-phosphate here. Aldolase B gives us glyceraldehyde. This is how I remember it. Aldolase A, B, glyceraldehyde 3-phosphate. Aldolase B gives us glyceraldehyde. This is the pathway, the first pathway. And this is the second pathway. It's not clear, even though I tried to make it clear, but the textbook I had, can you see it? Can you open your, okay. So we have 2 slides, I said, that will cover 90% of the lecture.
This is the second slide?
This is the second slide. So if you look into it, I tried to summarize for you most of the things, regulation of into this pathway. One thing before I continue, I wanted to mention to you, is that fructose does not promote the secretion of insulin. Why? Fructose does not promote the secretion of insulin. I already answered you. Glucokinase and PFK1 and bypasses it. Right? So it does not promote because it doesn't need it. Glucose needs insulin because it needs to stimulate PFK1 and glucokinase. Whereas fructose does not need stimulated. Also, when is insulin secreted? When glucose goes up. Does glucose go up with fructose?
No.
Does not. Why? What do you think? Glycolysis occurs? And also, can we utilize this for glycogen synthesis? Can we utilize fructose for glycogen synthesis? These are common questions we ask. Can fructose be utilized for glycogen synthesis?
No.
Yes, it can go backward. Notice here pyruvate. Why is it that fatty acids cannot be utilized for gluconeogenesis? Fatty acids.
It can be transferred.
Because fatty acids release what? Acetyl-CoA. Acetyl-CoA, can it be reverted back to pyruvate? No, it's one direction.
Can be reversed.
So it cannot be reversed. So anything before pyruvate can be reversed.
But when it comes to pyruvate, no.
Pyruvate to acetyl-CoA. Once you make acetyl-CoA, this is when you're burning fat, you're releasing fatty acids, acetyl-CoA, coming from fatty acid, right? Fatty acid cannot be reversed to pyruvate. That's why we cannot produce glucose from fatty acids. Yes?
You said that fructose can be used for glucogenesis?
For glycogen synthesis, for gluconeogenesis, yes we can. Because we can reverse it back. Yeah, of course.
You said that fructose can be used for glucose synthesis, right?
Yes, can go all this way.
But then it's going to meet PFK1 and glucokinase, so then it needs insulin.
But is this regulated by insulin? Is it regulated by insulin? We said insulin regulates what? PFK and glucokinase.
It's still needing glucokinase.
No, it needs phosphatase. Because it gets into fructose 1,6-bisphosphate by the phosphatase, fructose 6-phosphate, and so on. Right? It can be reversed. This is not regulated by insulin. I'm sorry, this is regulated by insulin, PFK1, but not the phosphatase. Glucokinase, different. Are we clear?
Doctor, I searched the enzyme for conversion of glucose. Is it phosphogluconease?
I like that dedication. Okay, so this is the second slide. Let's try and go through it. As I said, it's really significant because we're going to describe all the symptoms that we will see. For instance, can fructose, if you're taking too much fructose, can this lead to hypoglycemia? Fructose, if there's too much fructose,
Yes.
can this lead to hypoglycemia? Yes, but why? We're going to explain that. Also, what about people with gout? We haven't had nucleotide metabolism yet, right? Where we break down purine metabolism, purine breakdown into uric acid. Okay. Well, you're going to have it now. I think you're going to have it next semester. But also, you're going to have it in the third year. I just explained it to third-year students. And then it made more sense to them because they had more clinical information. So basically, this is what we call King's disease. Because they eat too much meat. So when they break down the DNA in the meat, that results in uric acid accumulation, and we end up with gout. You know what's gout? Have you seen gout? Pictures where basically on the joint, not only it's inflamed, but also toffee accumulation. You'll have that. But also, we have hyperuricemia. Have you heard about hyperuricemia? Which basically could aggravate joints and cause some pain in the joints. High uric acid. And why is it that we have these symptoms? Well, here's the thing. I have high uric acid myself. Why? Because I eat too much sugar, too much carbohydrate, too much chocolate. While I'm always working, I have to eat. This is a bad habit. But people who take too much carb, especially fructose, they will aggravate any joint problems. Rheumatoid arthritis and any problem with joints basically will be aggravated because of the fact that people who take in fructose will have uric acid, high uric acid. That's how it is. Again, the question is it good? I mean, are you telling us that if we take too much fruit, it's going to be bad for us? Yes. If you're drinking too much juice, that's bad. Everything is moderate. So we'll discuss why is it that people who take in too much fructose, that could be bad for you because that could lead to joint problem, could aggravate joint.
Fructose leads to high uric acid. Does that mean that too much fructose can lead to gout?
Because hyperuricemia, if you go beyond that 6.8 milligram per deciliter, that could result into gout. Hyperuricemia is associated with gout because uric acid forms crystals with salts, precipitates in the joint. That's where we end up with gout.
With too much fructose and too much meat leads to gout?
Over a long period of time. As I said, we call it the King's disease because they eat too much meat all the time in their food. As a result, this is all days, of course. This results into accumulation of high uric acid, and then this could lead to gout. Precipitation of this uric acid into urate precipitates in the joint. Okay, let's try to memorize this slide. We know most of it. It's the same slide like the one before, except I added the sorbitol. Let's review it. As I said, repetition should actually reinforce key facts. Now, we have glucose. Glucose can be converted to glucose 6-phosphate. In which pathway? both ways. Glycogen synthase, and then or glycolysis. Right? Glucose 6-phosphate gets converted to fructose 6-phosphate. Glucose 6-phosphate to fructose 6-phosphate by isomerase. I told you could have waited until the next slide. So we have fructose 6-phosphate. This is isomerase. Fructose 6-phosphate becomes fructose 1,6-bisphosphate by an enzyme called fructose 1,6-bisphosphatase. It's the same.
Yeah.
It's the same. This is the pathway. But also, I'm sorry, this gets converted by phosphofructokinase. This is the reversal. And this is what we said, PFK1 is stimulated by insulin. This is a regulatory mechanism. Now we have fructose 1,6-bisphosphate gets split into glyceraldehyde 3-phosphate by aldolase A and aldolase B, glyceraldehyde 3-phosphate, or dihydroxyacetone phosphate. Now, the dihydroxyacetone phosphate can be converted to glyceraldehyde 3-phosphate by the triose isomerase. We have the 2-phosphoglycerate, pyruvate, acetyl-CoA, and fatty acid synthesis. We already know this, right? Now, let's see what else did you add to it. Diet, we get fructose, right? Fructose comes from diet, whether it's sucrose or fructose as is. Two pathways. What did I say about hexokinase? All tissues,
Oh yeah.
but also non-specific. It can phosphorylate glucose, or it can phosphorylate fructose. Right?
Yes.
But it has higher affinity to glucose than fructose. It likes glucose more. And we have glucokinase, which is also stimulated by insulin, converts glucose to glucose 6-phosphate that's present in the liver, as I indicated. So now we have two pathways. Fructose can be converted to fructose 6-phosphate by hexokinase, but it doesn't like that because it likes glucose. So it's a minor pathway. That occurs only when we have really high levels of fructose. We're pushing this pathway. Right? Why? Because fructose in a major pathway gets converted by fructokinase into fructose 1-phosphate. Kinase, fructose 1-phosphate, right? Fructose 1-phosphate by aldolase B gets converted to glyceraldehyde, as I said. Glyceraldehyde, basically 3-phosphate coming from aldolase A, B, glyceraldehyde coming from aldolase B, as we indicated. So two enzymes here I need you to know. Fructokinase, aldolase B. Why? Because we have deficiencies of fructokinase, deficiency of aldolase B, inborn errors in metabolism. When there's a deficiency of fructokinase, we end up with essential fructosuria. When we have deficiency of aldolase B, we have hereditary fructose intolerance. This is a benign condition, so it's no big deal. We can easily manage. Whereas here, hereditary fructose intolerance, or HFI, that's serious. We need to take care of it. Now, another thing also, glyceraldehyde to glyceraldehyde 3-phosphate by triokinase. That's easy. The limiting enzyme for fructose metabolism is aldolase B. Why? It's not glucose. Simple. Fructokinase is active. Aldolase B is slow compared to fructokinase. Again, fructokinase is faster than aldolase B. So what does this result in? Fructose 1-phosphate accumulation. So we have accumulation of fructose 1-phosphate. Why? Because this is fast, this is slow, so there is accumulation of fructose 1-phosphate. This is like the bottleneck, where you have too much of fructose 1-phosphate but cannot get into glyceraldehyde because aldolase B is the limiting reaction. But also, this results into what? Fructose 1-phosphate. That's phosphate. Coming from where? ATP. Results in what?
And the block of
Low ATP, but also ADP formation and AMP formation, right? Because we took the phosphate out. We are sequestering the phosphate here into fructose 1-phosphate, which results in what? You have AMP, ADP. What happens to them? They get broken down into what? Uric acid, resulting in hyperuricemia. That's why if you're taking fructose, too much of fructose, you're sequestering the phosphate pool, you're trapping it, producing too much of AMP, ADP, that then gets broken down into uric acid, hyperuricemia. So this is why if someone has gout or has rheumatoid arthritis or joint problems, try to advise not to take too much fructose. That is from fruits, sugar. I mean, take moderate, because you still need the vitamins. You still need the other essential minerals and so on. But the thing is, you need to try to cut it down into moderate intake rather than loading into it. This is why in diabetes, can you advise to give more of fructose? What do you think?
No.
You're bypassing regulation right there. Everything is moderate. Everything is moderate. Are we clear about this pathway?
yes.
You remember it? Now we're going to repeat it, explain it over and over in the next slides. As I said, 90% coming from these two slides. First step, we said fructokinase, converting fructose to fructose 1-phosphate, right? This is the first reaction, phosphorylation of fructose. And this is done by two pathways coming from hexokinase or fructokinase, as we indicated. Fructokinase is the major pathway. Hexokinase, lower affinity to fructose, has higher affinity to glucose. Only when we have high levels of fructose, this enzyme gets into action, as we indicated. Now, the second reaction, cleavage of fructose 1-phosphate, to which metabolites? Fructose 1-phosphate gets converted to what? By aldolase B, glyceraldehyde. This is the second step. So, aldolase B cleave fructose 1,6-phosphate, produced during glycolysis to dihydroxysteroid phosphate, glyceraldehyde 3-phosphate. Aldolase B cleaves fructose 1-phosphate to dihydroxyphosphate, and which can directly enter into glycolysis, gluconeogenesis, and glyceraldehyde. This we already mentioned. Here's a question for you. Why is it that the fact that knowing that the utilization of fructose by fructokinase, then aldolase B bypass the steps of glucokinase and PFK1, which are activated by insulin? This could explain why fructose disappears from blood more rapidly than glucose in diabetic subjects. Why? Diabetic subjects, insulin is insensitivity or lacking in type 1 diabetes, and it relies on insulin, whereas fructose doesn't need insulin. So if you take the fructose, basically it can easily disappear in circulation. So it's good, but as again, in a moderate amount.
If we take too much fructose, it will cause hyperglycemia.
It will cause hyperglycemia, and also it will lead to, I did not discuss this pathway, sorbitol. Not hyperglycemia, it will lead, if you take too much fructose can be utilized here. Too much fructose will lead to hypoglycemia. Why? Hypoglycemia. Why? Because it's going to sequester phosphate, right? And ATP, basically, what happens? Is needed for what? We need ATP. We have high level of ADP, AMP. Low level of ATP. What do we need the ATP for? Gluconeogenesis.
Oh, okay.
This is why we end up with hypoglycemia. So if you have aldolase B deficiency, part of the symptom is going to be what?
Hypo.
Hypoglycemia, because you're questioning the phosphate as fructose 1-phosphate.
Doctor, I mean not the glycemia, the uric acid will be called
Uric acid hyperuricemia. Okay? Again, why is it that people lacking aldolase B will end up with hypoglycemia? Because they're sequestering phosphate as fructose 1-phosphate. So we have high levels of ADP, AMP that could get converted to uric acid. At the same time, low level of ATP. Right? Because we're not producing ATP, we're sequestering the phosphate into phosphate 1-phosphate, fructose 1-phosphate. As a result, gluconeogenesis is lacking. As a result, we end up with hypoglycemia. So aldolase B deficient people have hypoglycemia. See, biochemistry is not boring after all. It can explain all these
True.
symptoms and pathways.
But not on the tests. That's for sure.
Well, I'm trying to simplify it. I don't think I can simplify it easier than this. This is,
Thank you.
I mean, as I said, we're going to repeat the same 2 slides over and over. But one part that we forgot to mention is the sorbitol. Let's just describe the sorbitol, because there are 2 enzymes that we will discuss. Why is it that we have a lot of damage caused by fructose or glucose? Both. When we have the damaging effect of type 2 diabetes is hyperglycemia. You take hyperglycemia away from diabetic patients, no complications. But why? Because of keyword sorbitol. What happens with sorbitol? Simple. Fructose, high fructose with sorbitol dehydrogenase. From the name, dehydrogenase involves NADH. Sorbitol dehydrogenase, we end up with sorbitol. Sorbitol with reductase, aldose reductase, NADPH is involved, will lead to the production of glucose. So fructose can be converted to glucose. At the same time, glucose, so you have hyperglycemia, can be converted to fructose, to sorbitol. Reverse. Sorbitol accumulation leads to osmotic pressure on the cell. That osmotic pressure causes the damage to the cell, including cataracts, eye complications, kidney complications coming from increased osmotic pressure coming from sorbitol accumulation.
That's why when we eat too much sorbitol that causes damage of the epithelium, it causes diarrhea.
It affects the kidney, it affects the GI, it affects everything. It is because of sorbitol accumulation. And that could be resulting from glucose, hyperglycemia, or fructose. Both can lead to sorbitol accumulation. So when I say, even for diabetic patients, if you say, let's give him fructose, because fructose is not going to induce hyperglycemia, but it's going to give you sorbitol as well. That's why still everything in moderate amount. Glucose, you need insulin. That's lacking in diabetics. So let's give moderate amount of fructose, but not too much, because then you're still building sorbitol that's coming either from glucose that you're trying to avoid, but then fructose will lead to sorbitol. Does it make sense? Okay, let's just go through these. As I said, most of the slides from these, the rest of the slides coming from these 2 slides. Now, kinetics of fructose metabolism, we already discussed it. This is just a review for you. Fructose 1-phosphate, glyceraldehyde, dihydroxyacetone phosphate, and this is glyceraldehyde by triose kinase, glyceraldehyde 3-phosphate, dihydroxyacetone phosphate can be converted to glyceraldehyde 3-phosphate by an isomerase, TEM. Now, another thing, so do we need fructose? What do we need the fructose for? Here, this slide. We have fructose 6-phosphate, right? Either we take this pathway for glycolysis, or fructose 6-phosphate itself coming from the hexokinase in other tissues, all the tissues. What we make is glucosamine. Glucosamine are needed for glycoproteins, glycolipids, proteoglycans. I got asked about proteoglycans versus glycoproteins. What are the differences between them? Well, people think that proteoglycan could be part of glycoprotein, but the way to differentiate between the two, from the name, proteoglycan, proteo, protein core, surrounded by polysaccharide carbohydrate. Again, proteoglycan, protein core, surrounded by carbohydrate. This is proteoglycans. And it is high in carbohydrate because it's core surrounded, all directions. So it's around 50 to 60% of carbohydrate in the proteoglycan. Glycoproteins, it is basically carbohydrate attached to proteins. That's how you remember it. And it's around 10%. There are some people, references I've seen, where they reversed it to 90% glycoproteins and so on. But these are the most common. I mean, the percentage is 50 to 60. They vary. Some have 90%, some have 10%. You cannot really make strong statement where say it's exactly 50 to 60%.
Debatable.
Majority, most of them. But here we have protein core surrounded by carbohydrate. We have carbohydrate attached to proteins. Okay? So we do have the N-acetyl glucosamine phosphate required for these glycoproteins, proteoglycan. What are these for? I mean, when I say glycoproteins, proteoglycan, give me the simplest thing that we found these. Where do we find them? In the extracellular matrix, around the cells. They're loaded with these.
As a gas.
As what?
Gas.
Okay, we talked about high fructose diet. It's just, as I said, this is just a review. High fructose diet leads to sequestering phosphate. We end up with hyperuricemia, as we indicated. Because of that, we have high AMP, ADP that get converted to uric acid. And you will have a full lecture about this pathway, purine breakdown. Disorders of fructose metabolism. We already discussed these. We said fructokinase could be impaired, deficiency, or aldolase B. With fructokinase deficiency, I told you it's benign condition. Why? We have accumulation of fructose. And when we have accumulation of fructose, it can go the other pathway through sorbitol, right? Or it could go through the hexokinase. So we have alternative pathways. This is essential fructosuria resulting from fructokinase deficiency, inborn error of metabolism. Another deficiency, aldolase B, which is hereditary fructose intolerance. That's more common, 1 in every 20,000 births, and could cause severe hypoglycemia. I told you why. Because of what? Sequestering phosphate, low ATP, low gluconeogenesis. Then we have other conditions. Why do we have here, if we have aldolase B, we have a problem? Because accumulation of what?
Fructose.
Fructose 1-phosphate, but also fructose can be, what happens to it? Going through the sorbitol pathway. Sorbitol is what causes osmotic pressure, causes all these damaging effects that we see in diabetes as well. Hyperglycemia could lead to sorbitol in diabetes. Fructose accumulation could lead to sorbitol. Sorbitol increase in osmotic pressure, all these complications and so on. So the two defects, hereditary defects of fructose metabolism, I already talked to you about it. Essential fructosuria, hereditary fructose intolerance, we discussed it. Conversion of mannose to fructose 6-phosphate. Actually, this slide should come to after the following slide, this one. Conversion of, I'll get back to the mannose. Conversion of glucose to fructose via sorbitol. We already discussed this pathway, this way, right? We have accumulation of sorbitol coming from hyperglycemia. Which enzyme? Aldolase reductase. And this is the conversion of glucose to fructose by sorbitol, aldolase reductase, sorbitol dehydrogenase, fructose. So it's, as I said, the rest of the slides are just a repetition of these two slides. Now let's go back into mannose, as I said, I'm not sure why I misinserted this slide. Conversion of mannose to fructose 6-phosphate, we already discussed this. Mannose, what did we say about hexokinase? Non-specific, fructose, mannose. So hexokinase will convert it to mannose 6-phosphate. Mannose 6-phosphate by an isomerase converts it into fructose 6-phosphate. That we already mentioned. This slide should be actually moved after. Okay, here's the thing. Hyperglycemia, sorbitol metabolism, we said it induces sorbitol accumulation, right?
Yes.
Now, if we have diabetic patients, we have glucose transporter, right? GLUT4, responsible for glucose transport, controlled by insulin. But there are many other tissues that have glucose transporters without insulin control. So glucose can freely get in. That includes seminal vesicles, lens, nerve, kidney. Why do we have complications with type 2 diabetes? We have hyperglycemia, and they get into these tissues without any insulin regulation. Freely access. We're converting glucose from fat, muscles, into these tissues. As a result, what happens? Sorbitol accumulation, hyperglycemia gets converted into sorbitol. We have high osmotic pressure, and we have all these complications associated with the retina, lens, kidney, nerve cells, because of sorbitol dehydrogenase. This is sorbitol dehydrogenase. We have accumulation. This is fructose. These are for people who are there is a reduction or low sorbitol dehydrogenase. This leads also to sorbitol accumulation, and we have all the complications. So it could be through hyperglycemia, glucose getting in, forming sorbitol, and also in these tissue we have deficiency of sorbitol dehydrogenase, so there's accumulation of sorbitol. So two things here. Hyperglycemia gets converted to sorbitol. Tissues that are low or absent in terms of sorbitol dehydrogenase leads to sorbitol accumulation, and that's when osmotic pressure gets into play, causing all the complications and so on. Galactose metabolism quickly. It occurs in the liver, and galactose coming from where? Galactose? Milk, right? Galactose is sugar. So these are the importance of galactose. Here's the pathway of galactose that we already studied, but one enzyme that we need to look at. Galactose to galactose 1-phosphate, right? Through which enzyme? Galactokinase. It's a kinase. Galactose 1-phosphate gets converted to glucose 1-phosphate. I know you all said isomerase, but I said no. It is uridyl transferase. Galactose 1-phosphate, uridyl transferase. And there is inborn error metabolism where there is deficiency of uridyl transferase as well. So uridyl transferase converts galactose 1-phosphate by reacting with UDP glucose that gets converted to UDP galactose. UDP glucose, does it ring a bell? Glycogen synthesis, right? That's the active parent molecule that gets converted into glycogen, UDP glucose, right? So UDP glucose gets converted to UDP galactose, which in turn can be converted to UDP glucose by an epimerase. So epimerase right there, whereas here we have uridyl transferase. We have glucose 1-phosphate. Can we utilize glucose 1-phosphate for glycogen synthesis? Yes. Glucose 1-phosphate, but also we can convert it by a mutase to glucose 6-phosphate for glycolysis. This is everything I described in this pathway. So, disorders of galactosemia, high galactose levels, basically, because of three enzymes we just mentioned: galactokinase, uridyl transferase,
Or epimerase.
and epimerase. These are three inborn errors of metabolism. And because of that, we could end up with cataract, liver failure, mental retardation, galactosuria. And basically, this is the same pathway. We said galactose 1-phosphate by which enzyme? galactokinase. Galactose 1-phosphate with UDP glucose, we convert into glucose 1-phosphate, and we produce UDP galactose, right? Now, notice here that UDP glucose can be converted to UDP galactose and vice versa. It's a reverse pathway by an epimerase. So we have 1, 2, 3, inborn error metabolism. So let's see what happens if you block, if there's deficiency at galactokinase. There's going to be accumulation of what?
Galactose.
Galactose, and we have galactotitol. What is galactotitol? I just wrote it down for you. It's sugar alcohol breakdown product of galactose. Why do we need to know this? Because this is how we screen for inborn error metabolism. We look into metabolites. We measure galactose. We measure galactotitol. We measure galactose 1-phosphate. Can we do that? Yes. This is where the magic of mass spec. Metabolites. We can measure all the metabolites in the body, in the cell. And I'm hopeful within 1 month we're going to have our first mass spec down in the lab. Costs around 2 million riyals, but it's going to be powerful because we could basically measure all these metabolites in any tissue. As a matter of fact, this is called MOL-TOF. There's MALDI imager. This is new for, I don't think you're aware of that. As the surgeon dissecting the cancerous tissue from tumors, what do we do usually? We send the sample biopsies for frozen sections and the pathologist to look at it. Now with this mass spec technology, the surgeon has a pen and he just touched any tissue and he can tell whether this is cancerous or non-cancerous because it could analyze all these metabolites and proteins and tell him whether this is cancerous or non-cancerous just by touching the tissue. Just by touching the tissue while he's dissecting. You can look at it, this is cancerous, you can dissect and so on. It's already FDA approved, it's already in the surgery rooms and so on. It's just amazing, right?
Yeah.
What's more amazing, if I tell you, I mean, this is the new technology. You have a slide. We use immunohistochemistry, antibodies to detect certain proteins, certain metabolites. If I tell you now the new technology, the same machine, it's called MALDI imaging. You spray it, and then you put that slide in that mass spec. It will give you all the proteins, all the metabolites in these tissues. Simple, within 5 minutes. This is how powerful we're moving
So
into
we
this.
don't need to study.
Is what?
We don't need to study this.
But you have to understand. I mean, how do you know
pen
that
understands.
galactositol or galactose is up or galactose 1-phosphate? But it would be nice because if you have conditions that you take this slide and you see all the pathways that are affected, and there are softwares that can put it all together for you. This is the new era of metabolomics, proteomics, and so on. Anyway, so we have increase of galactose, galactositol. What happens if we block the uridyl transferase? We're going to see accumulation of galactose 1-phosphate. What happens if we have epimerase? We have galactose 1-phosphate and UDP galactose high. Okay? Finally, I'll conclude. Lactose, let me just finish and I'll take a question. Lactose synthesis. Why do we need lactose synthesis? For women to produce milk. Right? Now we have two proteins. Galactoside transferase